WSRE presents Food for Thought, in-depth examinations of political, social, cultural, and scientific topics. In November 2010, former NASA astronaut Rusty Schweikart spoke on the topic, Deflecting an Asteroid. His presentation was recorded at the Institute for Human and Machine Cognition in downtown Pensacola.
Tonight's topic is nearly as interesting as the speaker. Without further ado, let me introduce Rusty Schweikart. Thank you.
Thanks, Ken. Okay, well, good. We're in good hands here, Ken. It looks like the AV works and the picture came up, so there's no longer any excuse. So let me thank all of you for coming tonight. We're going to be moving pretty fast. I'm going to tell a few stories, and I hope that they will engage you. The title of the talk, actually one I sent in a couple of months ago, and so my talk only approximates what the title says, but Deflecting an Asteroid is the fundamental subject. And I threw in a subtitle which gets a little more to some of the questions that I'll be addressing tonight, which is, why the rush? Well, of course, one can always look at an asteroid impact from what I call the Wall Street perspective, which at the bottom, for those who can't see, it says, I suppose you'll expect a bailout. But a number of us felt that this was probably not a very reliable methodology. So I want to share with you basically why, for the last decade of my life, this has been an obsession for me. It's been basically, and I want you to know, in full retirement, nevertheless 40 to 60 hours a week for 10 years. Let me just say that's been contributed. Thank you. But it has been a major part of my life, and what I wanted to share tonight was going into why in the world, after a lot of things that you heard Ken say that I did and other things, why did this bite me this way? Well, if we go back into the mid-90s, you may recall that was about the first time when people were beginning to discover, especially some people in France and others at University of California in Berkeley, were beginning to, for the first time in history, discover that there were planets around other stars. Now, we always thought that was the case, but nevertheless, that was the first time we had evidence. Now, of course, we have over 500 stars. But NASA, as a result of that and other activities that were going on in biology, started this whole field. It's not really a discipline, but basically it's a very broad field called astrobiology. And astrobiology really hooked me at that time. The concept is great. It deals with all those things that we all asked as kids. What is life? I'll read it it goes too far to the bottom here, but what is life? Where and how did it emerge? What is its history? What is its future? And what is the relationship of life with the larger universe? These are big questions, and it's an incredibly active field. You don't look at this field for very long before you come to the realization that in terms of life on Earth, impacts by comets and asteroids in the early formation of the Earth, or shortly after the formation of the Earth, and ever since have played a very large role in both the development of and the evolution of life on Earth. And so around 1998, I ended up asking this question of, what really happened to the dinosaurs? I'll just read this. The real reason the dinosaurs became extinct, this dress makes you look kind of fat, right? Well, that's one person's interpretation of what might have happened, but of course, around that time, there was a pretty wide acceptance of the fact, or the idea, the generally accepted fact, that in fact, an asteroid impact was what wiped out the dinosaurs. So again, if you can't read this from the back, you know, we got the one dinosaur looking through a telescope, and he says, "Whoa, dude, check this out, this awesome asteroid. It's getting bigger by the second. Hurry up before you miss it," right? Pardon me, I'm looking for a laser pointer. There it is, sitting right there. Okay. So we knew, of course, around this time that an asteroid, it was thought or a comet, but much more likely an asteroid, in fact, is what wiped out the dinosaurs. And so one evening at the Morrison Planetarium in San Francisco at the California Academy of Sciences, a geophysicist, Professor Norm Sleep from Stanford University, was giving an evening lecture, not unlike this. And I decided, great, I'd like to hear what Norm has to say about impacts. As a geophysicist, his specialty is impact dynamics. And so he was going to lecture on the history of impacts in the early Earth and in the formation of the Earth. So this is what we're talking about. Asteroids which come in from space at tremendous velocity and impact the Earth, whether in the ocean or anywhere else. And in fact, in the early days, it was on a probably sterile Earth, in fact, after the sun ignited, the water which we depend upon and which, of course, enabled life on the planet, as well as hydrocarbons, arrived on Earth because of the impacts of comets and asteroids in the early Earth. And so these objects have played a key role in the development and enabling life on Earth. But of course, once it was established, then you're dealing with a threat to the life that's taken hold. And that is part of what Norm's lecture was. Now, Norm had two major takeaway points, at least for me. I mean, it was a very, very interesting lecture. But the two big things that I learned from it, yes, let me go to this slide. Let me just break a brief moment to remind people that asteroids are not things that orbit around the Earth. Asteroids orbit around the sun, along with the planets. So we've got Mercury, Venus, Earth, Mars, and the orbit of Jupiter. And the main belt of asteroids in green, largely well-behaved between the orbits of Mars and Jupiter. But these red dots are asteroids which have been basically perturbed out of the main asteroid belt. And these red ones, whether they're in here or red dots out here, all of these red ones are ones that come across the orbit of the Earth, that orbit the sun, but they cross the Earth's orbit. This is sort of a snapshot, so you don't get the dynamics. This one gives you a little bit more of a feeling of the dynamics. And so here you have, again, Mercury, Venus, and Earth's orbit sort of figuratively placed. And now you've got those snapshot dots are now moving. And of course, what we're talking about in terms of an asteroid impact, and let me just take the orbit of Mars because it's a little bit easier to see, but where you have the orbit of an asteroid crossing the orbit of the Earth, let's say, but just take it out here, you have the potential, on the diagram here, you have a two-dimensional impact, or two-dimensional intersection. But of course, generally speaking, there's the third dimension, there's space between the two objects at that intersection. But for a small percentage of those objects which cross the Earth's orbit, there is no third-dimensional room. It's a three-dimensional intersection. And so what you want to realize is that when there is a three-dimensional intersection, it's simply a matter of time before the Earth and the asteroid are in the intersection at the same time. And that's what we call an impact. So that's just a reminder of what we're talking about. You don't want to think about Earth orbit. This is way out. This is deep space. We're talking about things that go around the sun. Okay. So the two big points that Norm had that I took away were, one, this is not something that happened way back then. This is an ongoing process. And one of the ways in which he illustrated that was to take the demise of the dinosaurs, which some people will remember was 65 million years ago. And indeed, that seems like, you know, way, way back in history. But what I'd like to do is just have you guess here. You know, if we talk about the universe, or not the universe, but the solar system being 1 year old, and this is midnight on December 31st, when was it that the dinosaurs got wiped out? Was that like, you know, March or maybe June? Or
11:30 p.m.
On the 31st? Not quite, but December 27th. Right, December 27th was 65 million years ago when the dinosaurs got wiped out. So these things are going on all the time. We're still in this very same process that started back right after the formation of the solar system. So we're not going to run out of, we're not going to outlast asteroid impacts with the Earth. Now, I'm not going to get technical here at all, but if you can either, if you like graphics, look at this diagram where you have size across the bottom, and here's this KT impactor, or the big impactor that was about 10 kilometers in diameter, or about 8 miles in diameter, that hit back there 65 million years ago off the coast of Mexico, off the Yucatan coast. And that kind of object is still circling around, but not very many of them. What you're talking about is a range of objects from, say, 10 kilometers in diameter down. This is 1 kilometer. That's, excuse me, that's 10 kilometers, 1 kilometer, 100 meters, or 10 meters. So give you the idea of the scale. And between that object and down here, about 25 meters in diameter, is the range of objects which can do very serious damage on the ground if they impact. And there are many of these objects. Now, of course, the bigger ones, there are very few. There's only 1 or 2 down there at that size. But when you get up here to these smaller ones, there are far more of those, and there's about on the order of 10 million of those, which, in fact, if we were in the intersection at the same time, can do serious damage on the ground. If you like that in tabular form, you can see at the bottom that the big one, the Chicxulub impact that wiped out the dinosaurs, was about 100 million megatons, for those of you who know what a megaton is, a megaton of TNT, or let's say a relatively sizable nuclear weapon is a megaton. And that impact was the equivalent of 100 million of those going off at one time in one place, all right? So the bad news is it's 100 million megatons. The good news is it only happens one time every 100 million years, okay? So it's not exactly a frequent event. But if you think about the universe, or not, again, pardon me, I keep slipping into the bigger picture. If you think about the solar system being 4.5 billion years old, then in fact, there were 45 of those suckers that have occurred in the history of the Earth. So even though there's a lot of time between impacts, 100 million years, nevertheless, the Earth has gotten hit by ones that big 45 times. Now, you might want to ask a question, well, let's just say, what's the probability of one hit? How big would that one be? That would be about 200, or actually about 120 kilometers in diameter, or something like 80 miles in diameter that hits the Earth, okay? And that probably happened one time. I'll mention that in the next slide also. If we go to the smaller size now, what you're talking about there is something like 1 megaton, okay, at 25 meters in diameter, something perhaps the size of this building, a bit bigger than this building if you wrapped it into sort of a ball. Those happen about once every 200 years. And the last one of those that happened was about, in fact, it was 101 years ago in June. It happened in Siberia in Russia, okay? So that gives you an idea of the size and the frequency of these things. The smaller they are, the more frequent they hit. The larger they are, the less frequent they hit. But they hit, and they will hit We've been hit millions of times by these objects, and we will be hit again. So it's only a matter of when, not if. Okay, now the other point that Norm made is the immense energy. I shouldn't say the other point he made. He made lots of points, but the other one that got me was the incredible amount of energy you're talking about when these things impact. I'll try to illustrate this a little bit graphically. If you take a picture, a nice scene somewhere out west, say, and you can see a little mountain range here, let's just say it's something like, 20 miles away, 18 or 20 miles away on a fairly clear day. Let's now take a cross section of that. And now everything below that line is below ground, if you will. Okay, just picture we're just looking underground across there. And an asteroid comes in, and what I've picked is, again, because of the dinosaurs are a very popular subject, so I picked a 10-kilometer diameter asteroid. That's actually Ida, but it's not 10 kilometers, but I've made it 10 kilometers. It comes ripping right through the atmosphere, and whether there's water here or not makes no difference to it at all. The speed is so high. You're talking coming in at something like 35,000 miles an hour, something like that. And when it hits, generally speaking, objects moving that fast are going to go down into the solid Earth about 4 times their own diameter. So before that asteroid came to a screeching halt, and it's a real screeching halt, it's down in the solid Earth 40 kilometers, 25, 28 miles down in the Earth. Okay, now if you think of something moving that fast, and in 2 seconds, going from 36,000 miles an hour to 0, you can imagine the amount of heat that generates and shock. And of course, it shocks all the ground around here. This arrow, by the way, is out at the distance of that ridge, 25 miles away or so. Okay, that object gets down there, and the amount of heat that is in there, in that rock, turns hotter than the surface of the sun. A good bit hotter than the surface of the sun. And of course, it explodes. And that's the 100 million megatons of explosive power. When that happens, something down there, that deep, explodes. It takes out a cone of Earth with it as it explodes, breaks it into everything from gas. It gasifies, it just vaporizes a lot of it. But the rest of it, it turns into everything from dust to pebbles, to rocks, to boulders, to mountains. The volume that we're dealing with here in a cone of that kind, first of all, as I said, we're standing, maybe 20 miles away, something like that. So we're up in the air. In other words, it reaches this far. The volume of that cone is about 30 plus Mount Everest. And what it's done is it takes that stuff and it throws it out into space. Some of it, a small amount of it, actually ends up escaping. It's greater than escape velocity. It goes back out into space. And that's not this object. That's Earth that gets thrown out into space. And the rest of it gets thrown on ICBM-like trajectories. I mean, you know what an ICBM does, okay? It launches, it goes up in a suborbital trajectory, an ellipse, and it ends up coming back to Earth a continent away or a couple of continents away. And while this is a communication diagram, it nevertheless illustrates what we're talking about. So you can picture literally, now let me just say the mass. I mean, I don't want to overwhelm you with numbers, but 10,000 billion tons of material is what gets excavated and thrown out. And the result then is literally billions of particles of all different sizes getting thrown out into space and coming down all around the world. So in addition to, and in fact far more important than the tremendous shock wave and the tsunami that's created and that kind of thing, which are all relatively local, what happens beginning nearby relatively soon, but anywhere in the world within 45 minutes, is you have coming down through the atmosphere these tons and tons and tons of rock, boulders, and everything else. And that's raining down, literally, all over the planet. And of course, like a shooting star, when this stuff comes down through the atmosphere at orbital velocity, it heats up, it ignites, it makes a flash, but now you've got so many of them, the whole sky turns to about 1,500 degrees. The result of that is that everything on the ground that is combustible bursts into flame. And so in addition to the tremendous shock and all of the rest of it, all around the whole planet, you now have global fires which put smoke and carbon into the atmosphere. So that's the kind of environment that occurs after one of these large impacts. Now, obviously, with a small impact, you don't have that kind of global phenomena. But when you have the big ones, you can appreciate why not only the dinosaurs, but 70% of all life got wiped out when that happened 65 million years ago. Now, what got to me in Norm's lecture more than what I've just told you, and it's probably because I'm a technical person, and I really have a gut feel after a while for thermodynamics. And one of the things that Norm pointed out as sort of a throwaway was that the sky ends up so hot. Not only do things just burn, flash into spontaneous combustion, but with the Chicxulub impact, with the one that wiped out the dinosaurs, about 1 meter of seawater boiled off. Okay, now if you think about 3 feet of water, just think of a pot a foot deep on your stove, and think of how much heat it takes to get that boiling, one, and then to boil it all the way down till the pan is burning on the bottom, right? That's evaporating that much water. Now multiply it by 3 to make it 1 meter deep, and now make it the width of the world, okay? The amount of energy involved in boiling off 1 meter of the world's oceans is just, it got me. I mean, so I was hooked at that point, this is something I'm interested in. So at that point, I kind of left the general idea of astrobiology behind, and I started looking seriously at impacts and asteroid impacts. Well, one of the final realizations that Norm Sleep gave me that night was this idea that all of us have, unless you've really been thinking about this, you probably share what I had as a school kid, and I think most school kids growing up today have. Everybody has heard about the tree of life, with very primitive organisms way down the bottom, and the branching of everything all the way out until you get human beings way out on the end here, and you got mammals in this section, and you got bacteria down here, and you carry what do you call them, archaea in one section, whatever. But there's a tree of life with all of this incredible diversity, with human beings way out on the end. Okay, and we picture this evolution of the tree of life as being a kind of monotonic process that started maybe with bacteria, who knows when, a few billion years ago, and it gradually diversifies, and here we are today. Not. Okay, that's not it. Because what happened was the following. Life started, that's still a good mystery, life started, diversified, bang. There's an asteroid impact. And it wiped out a whole bunch of that tree of life. Okay, 100 million years later, man, it's back up there blooming just like your garden when you take a machete to it, right? You turn around and, man, there it is again, spreading out and diversifying. Okay, bang, there's another one. Bang, there's another one. Okay, so periodically, in terms of things the size we're talking about, 45 times over the history of the Earth, and probably 30 of them while life was around, this is the kind of thing that happens. What I call the crazy cosmic gardener. You take the machete to the tree of life, and it gets whacked down. 100 million years, it grows up again. Bang, sometimes it gets knocked down almost to the roots, all right, with a really big one. The end of the Permian period was a good example of that. But there we are again. And now here we are today, and we're way up here. Pretty vulnerable out on the end. Even more vulnerable, if you think about it, are some of the living creations that have emerged out of us, like civilization, culture, world economy. I'll give you an example, okay? These things are even more sensitive than we as a species. So these impacts are very powerful influences. Now that's all been, in a way, I wanted to share with you why I got hooked. And I think you can get a sense of that. In a way, that's the bad news. But the good news is, and in fact, that was 1998 when Norm gave that lecture. In 2001, a bunch of us were well aware of the fact that we were looking systematically since 1998 for near-Earth objects. By the way, near-Earth objects are kind of a combination of near-Earth asteroids, which are about 98%, 99%, and a few near-Earth comets. You know, comets sometimes come into fairly near orbits. They don't necessarily have a, you know, from way out past Jupiter. Some of them have an aphelion, which doesn't go any further out than Mars. And so we call those near-Earth comets. As far as I'm concerned, you know, it looks like a duck. It hangs out with ducks. It goes quack. You call it a duck, right? So near-Earth asteroids, near-Earth objects, all one thing. So we were looking for near-Earth objects beginning systematically around 1998, about the same time that Norm was given the lecture that I heard. And you can see the blue ones here being the rate of discovery from 1980 over here on the left to 2010. Almost to today, that's October. And you can see that all NEOs, that is, you count everything, and that's the blue curve. The red ones are just the ones bigger than 1 kilometer in diameter. But we knew back here in 2001, for example, that we had been discovered that there was this knee in the curve, that we started looking for them, and lo and behold, you find them when you look for them. And there's all these near-Earth objects circulating around. And it was obvious to a number of us that it's only a matter of time before we find one that's got our address on it. And then what? You know, and nobody was doing anything about that. So a bunch of us formed B612 Foundation. B612, by the way, is the name of the asteroid from which the Little Prince and his rose came to Earth, if you remember the story of the Little Prince, Le Petit Prince. Okay? So we named our foundation in honor of the Little Prince, Little Prince's home. Okay? Asteroid. So in 2001, a bunch of us got together and said, look, we got two big questions. Can we do anything about it? Can anything be done if we know adequately far in advance that an asteroid is headed for an impact with the Earth? And the second question was, if the answer to the first one is yes, is there anything we, this little group of about 25 of us, could do about it? And I guess to my regret, to some extent, the answer to both was yes. Yeah, we can do something. Something can be done about it. Our technology now is adequate to literally do something about it. And number two, we decided, well, it wouldn't be right if we didn't try. And so for that reason, we formed a foundation. We've been working on that ever since. And so what I'll share with you is a little bit of that process and where it stands today. But the thing that's important, and you can appreciate the knee of the curve here when we started looking for these things, and it's still going up. But the number there is 7,000. As I mentioned in an earlier graph, the number of objects that can actually hurt us is something like 10 million. So we got a long way to go. And if we look at the next 10 years or so, actually I got 15 years here, out to 2025, and we take that point and run it down to here, then by 2025, we're going to have over 1 million objects in the database instead of 7,000. And over 300,000 of those will be like that one that hit in Siberia or larger. Okay? So with that discovery rate, you can bet we're going to find quite a number of those that look like they're going to hit us. And we may find some that actually are going to hit us. And there is a big difference between those that look like they're going to hit you and the ones that actually are going to hit you. And we'll talk about that in a moment. But that is the driving force behind all of the work that I and a number of others have been doing. The realization that we're going to find that many in the next few years, and there are going to be a bunch of them that look like they're headed our way. So enter defense. Okay? All right, what do we do about it? Well, if you want to protect the Earth from asteroid impacts, there are basically three things you've got to do. There are three components of it. Early warning, you got to know what's coming at you, or there's nothing you can do about it, right? So early warning is the sine qua non. Got to do that. Or as Don Yeomans at JPL says, there are three important things that you have to know if you want to protect the Earth from asteroid impacts. Find them early, number one. Number two, find them early. And number three, find them early. Okay? Absolutely right. Once you do that and you find one with your name on it, you got to have a deflection capability. Excuse me, let me go back up there. You got to have a deflection capability. And in my mind, and in our mind, B612 Foundation, this should be proven. Okay? You want to prove that deflection capability, not just say you've got it on paper. All right? We claim, in fact, that we do have that capability. It has not yet been demonstrated. Okay, and the third and the toughest part, you got to have what we refer to as a standing decision process. Because you can see something coming at you, there's something you can do about it, but somebody's got to make a decision. And that's not the simple question, or the simple answer you might think there. And we'll talk about that. Okay, so the best way I can deal with this without getting technical is to give you a good metaphor. So if you're ready, I'm sorry I'm not as entertaining as Bill Maher, but new rules, okay? Okay, new rules. Rule number one, the strike zone has been shrunk and moved to your head. Your head is the strike zone, okay? Number two, the baseball has been replaced with a rock, a very hard rock, okay? Number three, you got a world record fastball pitcher out there. World record, universe record fastball pitcher. Number four, one strike and you're out. You're dead. Number five, you're at bat forever. Okay? You never get out of the batter's box. All right, those are the new rules. Now, think about that for just a minute. Okay? The rock's coming at your head. Now, I'm going to propose that up until now, we've had our eyes closed. Now, we've been lucky, you and I mean, after all, I don't think there's anybody in the room over 100 years old. You know, that's a short time in the interval, even of the smallest ones that hit us, a couple hundred years. So it's not surprising that none of us have died yet as a result of this, okay? But if you're up there forever and you're talking about life and your grandchildren and other things, you know, your eyes being closed is going to be a guarantee that you become a dinosaur eventually. All right? Now, if you open your eyes, though, which is what we've done in the last 10 years or so, you can notice these things going by your head. Well, that's really pretty good, because if you can see them going by your head, what that says is you can duck. Okay? Or, in the case of this metaphor, you can foul one off. All right? You can swing and foul it off. And it takes a little bit of energy to do that, right? And especially if you're going to be at bat forever. So you don't just want to do it willy-nilly. You want to foul off the ones that really look like they're going to hit you. So now you look out toward the pitcher. You see these things coming. But guess what? With a really good fastball pitcher, you got to make a decision really early whether that thing is coming at you or not. In other words, you don't have perfect information. And if you wait for perfect information, guess when you get it? Immediately before you die, right? And long before you can get the bat off your shoulder, right? So when you see something coming at you, you've got to start swinging that bat to foul it off based upon a very early judgment when there's a lot of uncertainty of whether, in fact, you're going to get hit. The result of that is that you're going to swing 10, 50, 100 times when if you didn't do anything, it would miss you anyway. But if you're really good at swinging the bat, you're never going to get hit again. Okay? So you might swing 50 times, but one of those, if you didn't swing, probably would have gotten you. And that's sort of the situation that we're in with asteroids. We don't have perfect information that they're going to be at that intersection at the same time. But they might be. And we have a certain range of uncertainty, a probability of 1 in 50 that we're going to be there at the same time, or 1 in 100. And then you got to decide, do you act or not? Okay. So that's, now let me suggest that the process here, if you've lived that for just a moment, okay, the process is basically automatic. As soon as you have concluded this one's going to come close, you swing almost impulsively, especially when one strike and you're out, right? So you're not going to play a game. You're going to go ahead and swing. Okay. I'll come back to that in a minute. All right, how are we doing with our game? All right. So let's look at early warning, the scorecard. We're about a B- here, okay? We've been doing this early work that I showed you, and we have ways, in fact, Ken and I just finished a thing where we recommended to NASA a different kind of telescope that you put in space, and we can very rapidly begin to build the database up toward that 1 million objects that we know are out there statistically, but you can't protect yourself against a statistical thing. You got to protect yourself against a real pitch, you know? So you got to find these things, actual asteroids. So we have ways to do it, but we're not there yet. The answer here is just do it. And that's basically what we told NASA and the White House and the Congress. You know, just do it. We got to get this early warning system going. Okay, let's talk about deflection. Okay, first of all, break again. What's deflection? If you think about that three-dimensional intersection, deflection is pretty simple. What you do for deflection is you go out well ahead of time when you know that there is going to be you're both going to be in the intersection, or you think you're both going to be in the intersection. You go out there ahead of time, 10 years, 15 years, 20 years if you got that much early warning. And what you do is you very slightly increase the speed of the asteroid or decrease the speed of the asteroid. And then 10 years later, or 15 or 20, whenever it was going to be in the intersection simultaneously, the asteroid, depending upon whether you speed it up or slow it down, the asteroid will either get to and through the intersection before the Earth gets there, or the Earth gets through the intersection before the asteroid gets there. So you change the time of arrival of the asteroid. That's deflection, okay? So it's a very simple concept. Not so simple in execution, but a simple concept. Okay, how do you change the velocity of an asteroid? You run into it, okay? It's just like on the freeway, you know? Go up there and run into it. We did that with a comet. This is a picture of the Deep Impact spacecraft, July the 4th, 2005, ran into Comet Tempel 1. We didn't run into it to change its orbit. We ran into it to splash its guts out so that we could see what it was made of. But still the same, you know, the same mechanical thing. And that's what you do with an asteroid. Asteroids much smaller than that comet, but nevertheless, you run into it. And you can either run into it from the front, run into it from the back. You can speed it up or you can slow it down a little bit. All you need to do is change its velocity like 1/10,000th of a mile an hour. Okay? But it's pretty big, you know, you're dealing with heavy things. Now, the problem with this is that while it's pretty robust, it's imprecise. And in the end, what you want to do is put the asteroid in a very, very well-known orbit. You don't want to just make any old change in the thing. You want to put it in a very precise orbit, which is not going to end up just bringing it back to hit you 4 or 5 years later. And so while you do this first, the last thing you do is you use what we call a gravity tractor, and you're just using gravity from your spacecraft as a tow rope. You're not even touching the asteroid, but you pull up in front of it, and you stay there, and gradually your mutual gravity slowly increases the speed of the asteroid, or behind it, and it slows it down. But now you don't destroy yourself in the process, So you can measure the velocity change, and you can get the job done precisely. Okay, so that's deflection. The concepts are good. The technology is available. We don't have to go into a big technology development thing. Okay, so the scorecard on deflection, D-, because we haven't done anything other than what I just told you. You're now experts in deflection. Okay? Do you feel confident? I hope not. Okay. But it's early. A few of us have been working this until a few weeks ago. In fact, NASA didn't have the authority to do this kind of thing. It wasn't in their charter for them to do this. They're supposed to do space exploration and space science. This is not science, and this is not exploration. This is public safety. Okay? So just recently, the White House sort of said, not in as clear words as I would like, but nevertheless, the White House basically said, NASA, you ought to start looking at this and doing it. Okay? So we're going to get there, hopefully. It needs to be demonstrated. After you demonstrate the capability, then with the warning time, you're going to be able to build this stuff. So you don't have to have something standing by. You're not talking about an alert force or having things already in space. When there's a threat, you know what to build. You've done it. You've tested it. You know it works. You build it, launch it, and deflect the asteroid. Okay, so we got the first two things. They're going. We're not exactly feeling warm about it, but they're going. Okay, the third one. A standing decision process. Okay, this has to be, of necessity, collective decision making. You're talking about a threat to the whole Earth. And let me try to just I'll make a statement. We can show a diagram if you want afterward in Q&A or whatever, but I'll just make a statement. If in the process of eliminating the risk to everybody on Earth, there will be people of necessity put at a temporary risk who were not initially at risk at all. Okay? Think about it carefully. In other words, an integral part of deflection is changing the risk profile from somebody who was at the impact zone to somebody else who was nowhere near that impact zone. But when you're dragging that thing off the edge of the Earth, out into space somewhere, you're dragging that impact zone across people's backyard. Okay? The result of that is you're putting people at risk who were not at risk. You cannot reasonably or ethically do that without working with other people. Now, there's another good reason for it. And just picture for a moment that there's going to be an impact in the North Atlantic. Okay? Now, if you're looking at the planet, okay, from the asteroid point of view, headed for an impact, the impact point, what you're doing, in effect, with a deflection, is you're dragging that impact point, forget how the mechanics of it, you're essentially dragging that impact point across the face of the Earth to the right or to the left, okay, until it gets off the edge of the Earth. And then the Earth's not going to get hit. But you drag it to the right, you drag it across Europe and Russia on the way off the Earth. You drag it to the left, you drag it across Canada and the United States until it gets off the Earth. How do you do that? Who makes that decision? Do we race the Russians up there? Try to get there before they do? We get there and we push one way, they push the other way? I mean, you can't do that, okay? So this has got to be coordinated. You've got to work it. So here I am, little old me, in the back of the United Nations in Vienna, making a presentation like the one I'm giving you, saying, you guys got to get your act together. I've been doing that since 2006. Okay? The Association of Space Explorers, not the B612 Foundation, but the Association of Space Explorers, which Ken mentioned. We're a bunch of astronauts and cosmonauts from countries around the world. We can open almost anybody's door, one time anyway. Then you got to have something to say. But, so we took this on. We said, hey, look, this is a space issue. We're a bunch of astronauts and cosmonauts supposed to be doing good for the world. Let's take on this issue of trying to get the world to pay attention to this threat so that we can eliminate it. Now, I want to call your attention to what we're talking about here. What we're talking about is terminating the crazy cosmic gardener, firing the crazy cosmic gardener. If we do this job right, never again should the Earth be hit by an asteroid that will kill people on the ground or any other life. Okay? Now this process, mind you, has gone on for 4.5 billion years. And now we're arrogant enough to say, hey, with our technology and our brains, we have the capability of terminating a process that has gone on and shaped life on this planet for 4.5 billion years. And never in the future should it happen again. That's a pretty arrogant statement. I mean, you want to talk about the audacity of hope. That's pretty audacious, okay? But that we can do. And it doesn't take new technology. The biggest thing it takes, I mean, the technology is simple. You know, a few astronomers, a few more telescopes, a little bit, you know, a couple of space flights to prove the capability. But there's the issue, okay? And that issue, so where are we here? Scorecard, decision making, okay? Incomplete. We don't know what the grade is going to be here. The big question is down at the bottom. When you're standing in the batter's box with your head as a strike zone, and that's coming at you, and it looks like it's going to get you, you almost don't even have a choice. Reflexively, you swing the bat. Okay? You have an irrepressible survival instinct. Okay, there's the question. Is there a collective survival instinct? And is that survival instinct, to the extent that it exists, enough to overwhelm the geopolitical game playing and BS that goes on a day-to-day basis between people in the world? So that's the question that we're dealing with. And this is a scorecard that I've given you. Okay, now you may not like the United Nations, but here down at the bottom, for people who can't see it, all hat and no cattle, but my God, what a hat. Okay? That's the United Nations, man. You know, we don't like them. They can't make decisions. They're a bunch of, you know, self-serving. You know, you got your own favorite adjectives. It's the only organization in the world that represents everybody. That's a heck of a hat. But to get that system to make a timely and authoritative and crisp decision is one hell of a challenge. And that's what we've been involved in and still involved in. Okay, so I'm going to end here. I just want people, again, to reflect on what it is we're talking about. We're literally talking about, and this is serious. I mean, I'm not just giving an interesting lecture. This is work that we've been doing, serious work, with a lot of people now, including the United Nations, who are good people. They've taken ownership of this issue right now. Should get to the General Assembly in about 2 years from now. Okay, what we're talking about in reality is reshaping, ever so slightly, but significantly reshaping the solar system in order to enhance the survival of life on Earth. That's what we're talking about doing. All right? The way I have expressed it, for me, the way I like it is the following. It's likely that if there, and that's a big if still, if there is a community of sentient life out there in the universe, that its members have each faced this challenge and passed it. Okay? If you think about that. We humans now face this great test of admission to the space community. If there is other intelligent life out there, they had asteroids and comets as well. They wouldn't be around if they didn't pass this. So the question, in a sense, in a big sense, is are we going to join this community or not? Thank you. Okay.
Very curious on the point that you made about the asteroids and the comets bringing the capability of water on the Earth. How is it that with other planets that may have taken impact from asteroids and comets that the Earth would have as abundant of water as it does, but the other planets don't?
Well, the answer to that, I'm thankful for the thing because I don't have to repeat your question. The answer is the Goldilocks zone. We live in the middle of the Goldilocks zone. In other words, if you put water on Jupiter, it instantly turns into ice, or some of it sublimes. I mean, there's no liquid water. You go to Venus, and it's 800 degrees on the surface. It all boils off. You know, it's gas, and you can't have a good chemistry in a gaseous system. We happen to live in the middle of a zone, of the temperature zone, where liquid water is feasible. You know, it's not too cold, not too hot. You know, so that's the basic answer to that question. And again, water, you know, water is common throughout the universe. I mean, it's not unique. So where there is liquid, the search we're doing today for other planets, you know, the thing that's really got everybody going, everybody's looking for an Earth-like planet, which means not only the size of the Earth, but also one that's around its star at a radius where it's in the local Goldilocks zone. There's one potential candidate so far out of 500. So.
My question deals with the size of when it's hopeless, helpless, we don't have enough hydrogen bombs to deflect it. Do we have enough capability to deflect one that ended the dinosaurs?
Well, it's a good question. The answer right now would be no, all right? But again, go to the frequency with which you get hit by one that's 10 kilometers in diameter, and you're talking about once every 100 million years. Unless we're really, 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 really unlucky, that's not going to happen for a while, all right? The ones we're going to most likely have to deflect are the ones that are the smallest, and they're going to come in every 200 years. Now, let me point out, they're going to come in every 200 years, but again, think back again about you're going to have to act, you're going to deflect, you've got to swing the bat when it looks like it's going to hit you. So if our ability to forecast simultaneity in the three-dimensional intersection is 1 in 50, if the probability is 1 in 50, okay, then we're going to have to swing that bat when it looks like it's going to, when the probability is 1 in 50, and if we actually get hit once every 200 years, that means about once every 4 years, there's going to be one that looks like it's going to hit us. So that decision-making process that I showed you there in the United Nations, and the United Nations is not it. The international community, humanity, okay, has to make this decision. That kind of decision we're going to be confronting about every 4 to 10 to 15 years. That's the kind of frequency you have to make a decision whether to swing the bat. Even though you only get hit, if you just close your eyes, you're only going to get hit with a small one once every 200 years. But we don't want to get hit again, period. That's the point. So now, really big one? No, we're not going to be able to handle that. But up to, let's say, 400 meters in diameter or something like that, we can handle it now with existing technology. In fact, if kinetic impact is not adequate, we can blow off a nuclear weapon next to it. That heats up one side of the asteroid and pushes it in the opposite direction. You don't blast it away because there's no blast in space, but you end up with a neutron bombardment of the surface. It heats it up and pushes the asteroid the other way. And that's a little bit more powerful than kinetic impact. And that can handle things up to maybe a kilometer in diameter. And even those are only, you know, a kilometer in diameter we only see once every 10 million years. So, you know, these things are not likely. And as you find these objects, you find the biggest ones first, right? And so, frankly, by the time we're 15 years from now and we've got, found many, many more of these objects, there'll be basically none left, or maybe just a couple left, at 400 meters in diameter that we don't know about. So we'll have lots of warning for the largest ones, and very shortly there won't be a need to have sort of a nuclear standby capability. But in any event, hopefully by the time we're threatened by something that's 10 kilometers in diameter, in the next 100 million years, we'll have a technology which will handle it. Maybe we can all get together and wish it away, who knows, but whatever the technology will be. Yes, sir.
According to your calculation, what's the next big one that's coming? How much time do we have?
Well, have you ever been to Las Vegas? I mean, when is the next 00, on the roulette wheel? It's 1 out of 36 chances, right, that it's going to be the next one. But of course, you know, if you knew what the next one's going to be, so we could get hit tomorrow by a 10-kilometer object. Well, we really couldn't, because we're looking, you know. But we can get hit by something that's one of the small one. Any of them that we haven't found yet, we could get hit by tomorrow. Okay, or maybe 1,000 years from now that we get hit next by something noticeable. All you can say is, given the population, on a statistical basis, the frequency at which you get hit is such and such. And we can give you that information. That's those graphs I showed you. But, as I said, you have to convert, in order to protect yourself, you have to convert statistics into the real objects and then be able to predict when they're going to hit. So until we do that, we can't. Now what I can tell you is, with those 7,000 objects, okay, that we have found already, there are today only 309, as of this morning, which have a non-zero probability of impacting the Earth in the next 100 years. In other words, almost all of them have a zero probability in the next 100 years, because we can forecast that far ahead. We can predict that far ahead with the orbits. Almost all of them, but 309 have a non-zero probability of impact. Okay, how high is that probability? On average, it's something like 1 in 10 million. You know, in other words, we've only gotten a little bit of tracking on something, and it could be here, it could be here, it could be somewhere in between. So it looks like a very long, thin asteroid, you know, by the time it gets to us. So we have probabilities, and what we need is more and more tracking, because as you track, the uncertainty gets smaller and smaller until it's down to a point. And when it's a point, then you have a precise prediction.
NASA's role is changing substantially with losing the shuttle and privatization like Scaled Composites and other companies. What do you see as the future of NASA's role in this whole effort and our total space exploration in the next century, maybe, or 50 years?
Yeah. Well, of course, that's a big question and a very different one from this. So I'll take the intersection of that question and what I've been talking about, okay? The subject that we're talking about here is a fundamental public safety issue. And generally speaking, defense, public safety, those are, whether you're on the far right wing or the far left wing of the political spectrum, that's a government responsibility. So we're dealing here with something where you're not, private industry is not involved, except that, you know, you may hire somebody to do something, but the fundamental responsibility to do this, to make these decisions, to ensure that that safety can be provided to the citizenry of the world, is a government responsibility. So the question really is, who within government and how do they function? And again, as I said, just literally a month ago, the White House, after being directed by the Congress in 2008 to make a recommendation, was directed by the Congress to make a recommendation on who in government should have this responsibility, or in fact, more reasonably, how should the responsibility overall in this be allocated within the government agencies. And you can picture that while we're finding these objects, until we do have a full inventory and know of all the objects and tracking them, we may find something that's just about to hit us, where you don't have a chance of deflection. You can't, it's already 2 feet in front of you. There's only one thing you can do, and that's evacuate.